Hello, everybody. Welcome back to Mathematical Statistics. I am sorry about that delay. I forgot to erase my board, but it is done now. And today we start estimating what at least I've been waiting for this entire semester. We're going to have three major methods outside of the fourth method, which is what I call a common sense guess. And the first one is method of moments estimators. We're going to spend relatively little time on that. Then maximum likelihood estimators, which are the workhorse of all statistical estimators. And then the MVU, which is amazing, but doesn't always exist and isn't always easy to find, which is why the maximum likelihood estimators are used more in practice. So, so it sounds like we're getting to the MVU pretty quickly, but no, we've got some time to spend in maximum likelihood estimation and in machinery for the MVU. So today, oh yeah, big announcement. There's no homework today coming out. There's going to be no homework this week. So I was saying we have three main methods of estimation that we're going to cover. And the first is called method of moments estimation, or estimators. I'm going to write estimators because I want to introduce the acronym MME for method of moments estimator. That's what I use, and that's what a lot of people use, but some people use MOM for method of moments. And I think you're really going to like these because they're highly intuitive and very very plug and chug. You know, there's not a whole lot of thought that goes behind making one of these estimators. So it should be really easy if this were to come up on an exam after you've had some practice, of course. The idea is to look at population or distribution moments and equate them to sample moments. So first I want to define the population or distribution moments. I think we've actually talked about this a little bit, but before I do, the wording there. For us, we are looking at a random sample from a distribution because we're being really theoretical. But with data, your random sample is coming from a larger population, which, if you're going to use the math stat on it, is assumed to follow a certain distribution. So for us, I guess I wouldn't use the word population, but these are definitely called population moments. So population versus sample, or overall theoretical distribution versus sample. So here is notation and definition at the same time. We're going to use a mu, like our mean, sub k, to denote the expected value of x to the k. And this is going to be for k equals 1, 2, 3 on up. And these are, if you care, these are called non-central moments, which I don't want you to worry about at all. I only mention this in case you've seen moments before and you're like, whoa, that's not what I know as a moment. So central moments, which we're not going to use, would be to center these expectations around the mean of the distribution. Oh, it's cut off. Let me fix that. These are central moments, which again, we're not using, but in case you've heard the terminology, that's the difference here. We're just going to call them moments, and our default is going to be these non-central moments. So obviously, the first one is the mean for the distribution. The second one is the expected value of x squared, which you can compute if it is a tabulated distribution. You can take the variance and the mean and unravel that relationship to get the expected value of x squared, or you can put an x squared in front of the PDF and integrate. So then we have the idea of sample moments. These are things you compute from the sample. And we're going to denote them with a capital M for moment, and it's a random variable, so capital letter sub k, and it's defined to be 1 over n. So this is assuming you have a sample of size n. It's defined to be 1 over n, the sum as I goes from 1 to n of xi to the k. So when k equals 1, this is just the sample mean. And when k equals 2, this is averaging the values that have been squared. And the idea behind method of moments estimators is to equate population or distribution moments with sample moments and then solve for the unknown parameter. It feels really good and intuitive, especially once you see this example. So I'm going to let x1 through xn be a random sample, or IID, from the exponential distribution with rate lambda. And I want to find A. For this course, it would be okay to say V, but there are other ways people define method of moments estimators. I'll talk about that after the example. So it's not really unique, but I guess for the context of this course and our definition, let's find the method of moments estimator for lambda. Okay, so you want to write down some population moments. How many do you need? It is generally the number of unknown parameters, although sometimes when you're solving this little system of equations that's going to arise, things will cancel out completely and you'll actually need additional moments. But there's one parameter here, and I'm going to start with the first distribution moment, mu1. This is the expected value of x to the 1. And for the exponential, this is 1 over lambda. And then the first sample moment, which is 1 over n, the sum, as I goes from 1 to n of x sub I, which is x bar. So we're going to equate these. We're going to say 1 over lambda equals x bar. So big warning here, this is horrible. It's an intermediate step for algebra. That equation doesn't make any sense because on the right, I have a random variable and on the left, I have a constant. And this random variable is not going to be one of those boring random variables that's actually a constant. So really this doesn't make sense, but it kind of makes intuitive sense to think of them as the same thing. Then you solve for the unknown parameter and then you throw a hat on it so that it does make sense. Solve for the unknown parameter and put a hat on it. If we were in a physical classroom, I will have already erased this because I don't want anyone walking by from the hallway and thinking that's what we're going to do. Like that happens. But lambda, you can solve for that and you get 1 over x bar. As it stands, that also is horrible and doesn't make sense. But once you put a hat on it, then that is your estimator of lambda, which is a random variable. And we have found our first MME. Super easy, or at least super direct. You know, you write down a population moment and a sample moment, you equate them and you solve. And if you have 2 parameters, you're going to need 2 sets of moments. And as I was saying, possibly more if when you're solving a system of equations for multiple parameters, they don't completely determine the parameters. In some cases, things cancel out. We have already seen this as a common sense estimator for lambda for the exponential. It's one of the first things we looked at when we defined what it means for an estimator to be unbiased. And we saw that this is actually biased. So method of moments estimators do not have a lot of nice properties, whereas maximum likelihood estimators do, and that's why we prefer them. But you know, in fact, a method of moments estimator could actually give you something outside of the parameter space, which is really bad. But a lot of times it's actually the same as the upcoming better maximum likelihood estimator. And I want to go back to the word the as opposed to a method of moments estimator. Really equating any moments and solving for lambda will give you a method of moments estimator. So for this example, I could have looked at the second moment, the expected value of x squared, and I could have looked at the second sample moment and equated them and solve for lambda, and I'd get something different, but it would also be known as a method of moments estimator. I'm not out to trick you. I just want you to be aware that this is by far the most common way to produce a method of moments estimator, but other things can count as long as they came from equating moments. Equating fifth moments, if the mood strikes you, could be an MME. So let's do a 2-parameter example. And I really like this example because it's the gamma distribution. And up until now, we have had no estimators of alpha, only beta. And that's because alpha, it's in that gamma function and it's just hard to get at and interpret. So it's hard to guess at the estimator here, I think. So let's find MMEs for alpha and beta. 2 parameters, likely we're going to need 2 moments. Let's write down the distribution or population moments. Mu1 is the expected value of x to the first power, and that's the mean of this distribution, alpha over beta. Mu2 is the expected value of x squared, which is not quite the variance. This is the variance plus the expected value of x all squared. And if you recall or look at the table, this is alpha over beta squared plus alpha over beta all squared. I think that's going to be enough moments, but let's see. The sample moments, the first sample moment is always x bar. You don't have to write out that M1 equation, but I'm going to do it for our second example. So M1 is 1 over n, the sum as I goes from 1 to n of xi to the first power, which is always x bar. And the second sample moment is to average the squared values in your sample. So the sum from 1 to n of xi squared, and we don't really have a name or symbol for that. I mean, some people write like x squared bar, but they're defining that as they go. It's definitely not like a standard notation. So I'm going to equate the moments. Equate. I've got mu1 equated to m1, and that turns into alpha over beta equated to x bar. And then I have mu2, and that was this whole thing. So alpha over beta squared plus alpha over beta squared. And I want to equate that to m2. And let me put the x's in. This is alpha over beta squared plus alpha over beta squared equals 1 over n, the sum of the xi squared. Honestly, though, you might want to work with the M2 until the very end because we're going to be solving a system of equations and dragging around this big statistic. We want to solve this system simultaneously for alpha and beta. And in this case, we can do something easier than trying to isolate, say, alpha over here and then plugging it into the other one. And that's because we've got x bar equals alpha over beta. And if you go to this equation on the left, this is alpha over beta, 1 over beta plus alpha over beta squared equals that second moment. So when written that way, I can go ahead and plug in x bar for the entire alpha over beta. But you do whatever you have to do to solve for alpha and beta. And if it comes down to you just solving alpha in terms of beta and plugging it in, that's okay too. But going back to the right-hand side, this is going to be x bar 1 over beta plus x bar squared is equal to 1 over n, the sum of the xi squared. And solving for beta, I'm going to subtract this term over there, and I'm going to divide by this term, and then I'm going to flip everything. So beta turns out to be x bar over 1 over n, the sum of the xi squared minus x bar squared, which does not make any sense because the right side is a random variable and the left side is a constant. So in here, it was a matter of, oh, symbolic algebra, but put a hat on it. Put a hat on it and you have an estimator, and one that you should not be ashamed of. So let's go back and get alpha from this guy. I know that alpha is going to be x bar beta. So alpha hat is going to be x bar times our estimator for beta. So I'm going to take that thing in the rectangle in the lower right and multiply by x bar. And that's going to put another x bar in the numerator for an x bar squared over 1 over n, the sum xi squared minus x bar squared. Our two method of moments estimator and our first time ever estimating alpha for the gamma distribution.
Wow.
There is nothing more mechanical than method of moments estimators, especially if we've agreed to use the first moment and then possibly the second moment and not to do the central ones and the fifth moments. You know, if we agree to just do it this way, it is just write the first moment down, write the second moment down, you know, and just go. But we already saw an example that showed us that these are not necessarily unbiased. They're also not necessarily smallest variance. Under some conditions, we can talk about large sample properties and what they would converge to if they would converge in probability. But even that stuff is really hard to prove because method of moments estimation is just so clunky mathematically. Like it's easy to write down, but it either does not have some nice properties you would expect, or it does, but it's really hard to show them. Whereas in maximum likelihood estimation, we will definitely be proving all of the nice properties. And that's why we've got a ways to go before the OMVU. That's all I'm going to say about MMEs. They are nice in that they are intuitive. They do have some nice properties, and they have other purposes in statistics. For example, the next estimator we're going to talk about is called a maximum likelihood estimator. And in finding a maximum likelihood estimator, we have to do some optimizing using calculus and derivatives and setting the derivatives equal to 0. And if the problems get too hard to solve, you know, they're not bad for our nice known named distributions in the table. But if they get too hard to solve, those optimizations, then you're going to want to use some kind of like Newton-Raphson, some kind of iterative method to solve for them. And when doing that, it's good to have a decent starting value. We'll talk about that after we talk about maximum likelihood estimators. But MMEs, the method of moments estimators, are often used as starting values for numerical solutions to MLEs. So let's talk about MLEs. Maximum likelihood estimators, or MLEs. Definitely, there is not another acronym out there used for these. We have a random sample, x1 through xn, from a distribution with a PDF or PMF, f of x. I didn't close the parentheses because now I want to slowly start using a slightly different notation to really express the dependence on the parameter. So you don't have to do this, but I'm going to start doing it more and more. So I want to also, I don't want to just close this. I want to show its dependence on the parameter. Since this is all about estimating parameters, I'm going to put a semicolon theta. I have several reasons for using a semicolon. You will see a line. Some people use a line. I don't care if you choose to use that, but I think that's a really loaded statement if you know about something called Bayesian statistics that we're going to hit on at the very end of this course, just a skimming treatment of Bayesian statistics. In Bayesian statistics, you think of your parameters as random variables. And so this is actually like a conditional PDF. But right now, it's not a random variable, it's a constant. And it's just fixed, which is another reason people use this. Like it's given, it's known, it's fixed. But I prefer the semicolon notation, but I won't hold you to it. And the reason I'm using a semicolon and not a comma is because we are eventually going to be talking about a big joint PDF of something that involves multiple parameters. And so the semicolon separates the arguments of the PDF from the parameters, whereas everything else is separated by commas. So the idea behind maximum likelihood estimation is to choose the value in the parameter space that makes the observed data most likely. The observed data in quotes, because our data is x1 through xn. And I shouldn't use quotes there because now I want to say most likely in quotes. I'm going to take my quotes off of data. So here is a kind of silly, motivating example. I'm going to flip a coin, and note that I'm not saying a fair coin. I'm going to flip a coin 2 times, and suppose that the parameter little p is the probability you get heads on the coin on any one flip. Okay, and now this is the silly part. Suppose we know that p is in this set. Now, in real life, p can take on any value from 0 to 1 inclusive. It's a whole interval, but I'm going to use a little discrete set, which is kind of silly. I'm going to use 0.2, 0.3, and 0.8. I know, bear with me. Okay, so if we observe in our flips heads and then heads, it would seem that this is not strong evidence for anything. But if we had 5 flips and we observed heads, 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 it is looking like the probability of getting heads is quite large. Even though I don't have a lot of evidence here, I do have what I have. I've never seen tails. So looking at this, I think, and I'll formalize this, the value p equals 0.8 is most likely, not mostly likely, most likely. And if we observe tails, tails, I'm going to go with the 0.2 because it seems like heads is not really coming up. So if ... tails, tails, the value of p equals 0.2 seems most likely, but again, we'll formalize. And if we see maybe heads, tails, or tails, heads, it seems that maybe something in the middle, not directly in the middle, but given these choices, 0.3 is most likely. That's the idea behind maximum likelihood estimation, but I want to formalize this process. And I'm going to stick with this overly simplified example. And then after that, we'll take away this, this ridiculous assumption. So here we've got a model. The model is a Bernoulli distribution. If we label heads 1 and tails 0, I have a random sample of size 2 from the Bernoulli distribution. So if you see heads on the coin, record a 1, and tails, record a 0. So the model is we have a random sample, x1, x2, IID, a little redundant because I said random sample, from the Bernoulli distribution with some parameter p that is unknown, but is assumed to be one of those 3 values. So I'm going to look at the probability of getting like x1 equals 1 and x2 equals 1, I want to look at the probability that x1 is some little x1 and x2 is some little x2, and they're independent. So you can break this up into a product, and really this is a joint PDF. This is an f of x1 and x2, a joint PDF, or in our new notation, an f of x1, x2, semicolon p to show that dependence on the parameter, or even we eventually want to start using vectors here, which is usually going to be for a sample of size n, but a vector of length 2. And because these are IID, I get to multiply the individual PDFs. That's not an n, that's a 2. So fxi comma p. It's not one PDF squared because one of them has an x1 plugged in and the other one has an x2 plugged in. So I get, what do I get? I get p to the x1, 1 minus p to the 1 minus x1. And then if you want to use indicators, I can take on the two values, 0 or 1 with x1, and then I'm going to multiply by the same thing, but with x2. But in this case, since there's only these two values, 1 and 2, and there's only 3 values for the probability, I'm going to tabulate these probabilities like this. Okay, so over here, I'm going to put p 0.2, 0.3, or 0.8. And then up here, I'm going to put the data or the values of x1 and x2. And it could be 1 and 1, or 1 and 0, or 0 and 1, or 0 and 0. And then inside the body of the table, I'm going to put these joint probabilities. They're going to go right in the middle. So for example, the first one in the upper left corner is going to be p. So p is 0.2 to the 1 times the other, times, it's this, plugging in p equals 0.2 and x1 and x2 equals 1, right? This is going to disappear. This is going to disappear because if I'm plugging in ones, that's going to equal 1. This is going to disappear. This is going to disappear. So I'm going to have p to the 1 times p to the 1, and p in this case is 0.2. So I get, when multiplying, 0.04. I'm just going to fill out this table if I can. Not so good with the arithmetic. So if the probability of getting heads is 0.3, the probability I get a 1 and a 1 is 0.3 to the 1 times 0.3 to the 1, and that's 0.09. And this last probability is 0.64. Please let me know if you don't know how I'm coming up with these numbers. Do it in a direct chat if you're shy. I mean, it's fine. But continuing, for this entry, I'm going to use the p equals 0.2, and I'm going to have the 0.2 to the 1, times 1 minus 0.2 to the 1 minus 1, if you will. And the other PDF is going to give me 0.2 to the 0 times 1 minus 0.2 to the 1 minus 0. So I'm going to be left with 0.2 times 0.8, which is 0.16. 0.16. Moving down, the next one's going to be 0.3 times 0.7, that's 0.21. And the last one is going to be 0.8 times 0.2, which is going to be, oh yeah, symmetric here with the other p. Plugging in 0 and 1 for x1 versus x2, it's totally symmetric, so I'm going to get the same probabilities down the next column. And finally, plugging in 0, 0 for x1 and x2 for the different p's, I'm going to get 0.64, 0.49, that's going to come from 0.7 times 0.7, and 0.2 times 0.2, which is 0.04. So this is saying the probability we get x1 equals 1 and x2 equals 1, when the parameter p is 0.3, this is 0.09. And for the MLE, you observe the data. It is done. It is fixed. And if this is what you observe, the value of P that gives the highest joint probability of seeing that data, this is the highest probability in that column, and it comes from P equals 0.8. Whereas if you see like a 1 and 0, then this is the probability you would see that when P is 0.2. This is the probability you'd see that when P is 0.3. And this is the probability you'd see that when P is 0.8. So you get the largest probability of seeing that from P equals 0.3. And continuing in this way, we can write our first MLE. I'm going to call it P hat. If you're just doing an MLE problem, that would be good enough. If you're like in a problem where you're comparing the MME and MLE, maybe I would put a subscript like MLE, but you don't have to. I didn't do that in our previous examples. This is going to be 0.2 or 0.3 or 0.8. And it's going to be 0.8 if the x1 and x2 are equal to, 1 and 1. Actually, if I want this to be an estimator as opposed to an estimate, I do want it to be a random variable. I won't take off if you do this, but I want to make these values random. So it's like a random function, capital X1, capital X2, and it's going to be 0.3 if capital X1, capital X2 is equal to 1, 0 or 0, 1, and it's going to be 0.2 if capital X1, X2 is equal to 0, 0. But by having these be capital letters, then this is still a random. But I can put numbers in, and that would make this the actual observed numerical MLE. That motivating example is probably harder than what we're going to now, which is to take away that ridiculous assumption that P is one of those three values. Yes, we'll move to continuous stuff and derivatives, but it's going to be such an automatic process that, like the MMEs, this is your chance to really, I don't know, if you're having any struggles in this class, I think this is your chance to, this is definitely one of those new beginnings. So I want to formalize the MLE process. I want to make it so that I don't just write down a table and think about, well, if this coin is like this. We're going to formalize the process. And the first thing we're going to do is some notation. I might not make that one here. Notation. And a little bit more than notation. So suppose we have a random sample x1 through xn, a random sample from something. We're going to use f of x, semicolon theta, which is our generic parameter, to denote the PDF or PMF. So I've expanded this notation. Then I'm going to use, should have put use in the first one. Let me fix that. I'm going to use f of x with a vector, which is f of x1 through xn. This is going to denote the joint PDF of all n values in the sample. We really only talked about like two-dimensional joint PDFs so far, but the joint PDF for x1 through xn. And because they're IID, now they don't have to be IID, but just about everything we work with is going to be IID. So if you do have a random sample, then this joint PDF can be gotten by multiplying the individual PDFs. So this is a product symbol as I goes from 1 to n of f xi comma theta. And it is not one of the PDFs to the nth power because even though this function is the same for all I, the argument is not the same for all I. Okay, as an example, I still have more things to define here, but suppose that x1 through xn are IID Bernoulli with parameter p. The joint PDF here, I would instead use p instead of theta. This is going to be the product as I goes from 1 to n of the individual PDFs. And if you go grab this off the table or from your head, this is the product of p to the xi, 1 minus p to the 1 minus xi, and an indicator. The indicators are actually going to become relevant again in MLEs, 0, 1, xi. So I can simplify this, or at least massage it a little bit, into a p to the sum of the x's, and then a 1 minus p to the n minus the sum of the x's. Go ahead and write a couple of those out if you're concerned. Write out p to the x1, 1 minus p to the 1 minus x1, and then put x2 in. And you'll see that, not only is this getting summed up, but these ones are accumulating. And I have a product as I goes from 1 to n of these indicators. So the next thing I want to put on this list of notation, which is also, I want to make this notation slash definitions, is something called a likelihood function. Remember, our goal in this discrete case, this is the joint probability, is the probability of seeing this particular vector of x's for this random sample. And it's a function of p. And in MLEs, maximum likelihood estimation, you want to think of the data as fixed, and you want to find the value of the parameter in the parameter space that makes the observed data most likely. So the x's are thought of as fixed, and we are instead looking at this as a function not of the x's, but as a function of p. So this is how we define a likelihood function. Likelihood function. We're going to call it L, capital L. I have something else reserved for lowercase l's, capital L, and leaving this specific example again and going back to my general list, it's going to be a function of the parameter theta. And this is going to be one possibility, so not the likelihood function, but a likelihood function, is to take the joint PDF and just view it as a function of theta. Think of those x's as fixed. But another possibility is to take it to be anything proportional to. So that alpha here represents proportional to the joint PDF. This is proportional to, and that is proportional when thinking of it as a function of theta and thinking of the x's as fixed. So the x's are fixed and constant. And let me tell you why something proportional to the joint PDF is perfectly fine. Suppose you want to maximize this. I'm just making this up. It's going to come from that Bernoulli PDF, but like 3 times a little p to the sum of the x's times 1 minus p to the n minus the sum of the x's times the product from 1 to n of the indicators of the xi. So this is what I had before, but I added this 3. This is actually not a valid joint PDF. But as a function of p, it's going to have, like, p goes from 0 to 1, and it's going to have some kind of shape, maybe locked down at 0 and 1. And we want to find the place where this is maximized, and we'll call that P hat sub MLE. But again, this doesn't make sense as a PDF. It doesn't integrate to one. But I could use it as a likelihood. I said that you can use anything proportional to the joint PDF. So if this happened to be the joint PDF that you got, you could drop the 3 because that will just kind of rescale the function. I don't know, like this orange one is 1/3 of the original function in the circle. I should have given it a name up here. You could drop a 3 if it was in there. Equivalently, you could multiply by 3 if it was convenient for you. So this thing in the box, the 3 and all, is not a joint PDF, but is a valid likelihood. So if you want to maximize it, sure, the actual max value is going to change, but the place where it's maximized will not change. And if we're thinking of this as a function of P and the X's as fixed, this product of indicators is constant when you think of it as a function of P. So you can drop that whole messy part as well. I know that might be confusing. It'll be super clear once we do a few examples, and we're going to be doing a lot of examples of MLEs. So I think I can start probably the Bernoulli example. And in that example, I want to define some more notation. Okay, so suppose that I have x1 through xn, IID, Bernoulli with parameter p, and p is somewhere between 0 and 1. I'm not restricting it. And I want to find the MLE for p. The first thing I'd do would be to write down the PDF, or maybe you skip this part and go straight to the next step. But it is p to the x, 1 minus p to the 1 minus x, indicator 0 and 1 of x. The next thing I would do is, you know what, I should label these. So the PDF. The next thing I would do would be to write down the joint PDF, and that is f of the vector x and p, and you get that in the case that they're IID by multiplying the original PDF over and over again with the different xi arguments. So in this problem, this is going to be the product as I goes from 1 to n of p to the xi. We already did this, sorry. So let me just blow through this, right? And we got p to the sum of the x's, 1 minus p to the n minus the sum of the x's, and a product of indicators. Now write down a likelihood. You will never go wrong taking the whole joint PDF, but that could make your maximization step harder. So I would like to drop some stuff, and I am going to drop this. Thinking of this as a function of p, that is a constant. That's like the number 3, and it's not going to change where the maximum is. So I'm going to call this capital L of p, and I'm just going to take the parts of the joint PDF. You know, I'm going to drop any multiplicative constants. So this is constant with respect to p. I am out of time. Next time we want to maximize this, and the first thing I'm going to do is look at the log of this, because the log is a monotone increasing function. And although it will change the actual value of the maximum, we'll see that it won't change the location of the maximum. And taking the log almost always makes the maximization problem easier. So we'll do that next time, and then we'll do lots more MLEs, and then we'll start finding MLEs, properties of MLEs, and it's going to be awesome. This is where I really love this course. So please come back.